But we can find the derivative of this using implicit differentiation. We're going to just differentiate the whole thing. And let's go ahead and use a new page here. You can see this all right. So we've got the equation x cubed plus y to the fourth equal to 2x squared minus 2y cubed. And we're just going to differentiate both sides. So we're going to get 3x squared plus, and when I write this or when I think of this, I'm really thinking, okay, what's the derivative of some stuff to the fourth power, right? Because we're thinking of y, right? Y is pretending to be a function of x, right? It's not really a function of x, but we don't care. It's good enough. So I've got 3x squared, derivative of some stuff to the fourth is 4 times my stuff cubed times the derivative of my stuff. On the right-hand side, the derivative of 2x squared is 4x. The derivative of 2y cubed is, well, 2 times some stuff cubed is going to be 6 times my stuff squared times the derivative of my stuff. And then the rest is algebra. We're going to solve for y prime. So I'm going to group my y prime terms on the same side. It doesn't matter which side you pick. I usually try and pick the side that feels like I'm moving less stuff. In this case, it also will be the same either way. I also try to pick the side where more things are positive. Right? That's usually what I'm doing. The reason why I multiply by the derivative of y again is because I'm really using the chain rule. So what I'm really thinking about is y to the fourth is really like some function of x to the fourth. So for example, we could say that let's pretend y was equal to x cubed plus sine of x. It's not, but again, I'm just trying to make a point. Then y to the fourth is really x cubed plus sine of x to the fourth. And when we take the derivative of that, the derivative with respect to x of y to the fourth is the derivative with respect to x of some stuff to the fourth. Oh, sorry. Yeah. Let me do the thing where if you ever see like this here or this down here, just let me know so I can click on this and make it so you can see more of the screen. I always kind of forget to do that. So the derivative of some stuff to the fourth, well, we're going to use the chain rule and get 4 times our stuff to the third power, but then we have to multiply by the derivative of the stuff, which is 3x squared plus cosine of x. This is exactly acting like 4 times y cubed times the derivative of y. So the reason when we're doing this sort of implicit differentiation thing that we're multiplying by the derivative of y is because we are using the chain rule. Y is our stuff, and we're multiplying by the derivative of the stuff. Hopefully that offers some clarification there. So we are going to group the y prime. So after this first step where we take the derivatives using the chain rule, and really, I want to emphasize, it really is the chain rule, right? We're really like, oh yeah, y is a function of x, and we're just taking the derivative of this function of y and then multiplying by the derivative of y because y is a function of x. The rest is just algebra. Sometimes it's really ugly. This one's actually not that bad. I'm going to move everything to the left-hand side because that's going to keep more things positive. It doesn't really actually matter. It's just the choice I usually make. So I get 4y cubed times y prime plus 6y squared y prime equal to 4x minus 3x squared. Factor out the y prime. I might even do that in the same step, depending on how comfortable I felt with the algebra. And then finally, divide by 4y cubed plus 6y squared. So the derivative here at any point, xy, is 4x minus 3x squared over 4y cubed plus 6y squared. And then we're going to find the equation of some tangent lines at various points. So let's work first at the point 2, 2. Sorry, 2, -2. So here's the thing. We already know almost the whole answer. If we're writing the equation of a line, I'm always just going to write it as y minus the y coordinate equal to the slope times x minus the x coordinate. The only thing that we have to actually fill in is what the slope is. And the slope is just the derivative at the point. 2, -2. Oh, what's going on with this green pen here? Why are you getting green on me? It's terrible. Normally I would lick my thumb, like wipe it off, but it seems kind of weird to do that with the mask on, so I'll just deal with green fingers, I guess. Okay. So we're going to plug in 2, -2 to find what the value of the slope is. So y prime, you can either write it as evaluated at 2, -2 like that, but people probably usually write it more as y prime evaluated at 2, -2 like that. That's what that vertical line with this 2, -2 subscript means. It means you're just plugging in 2, -2. I don't know why this notation feels preferable, but it does. It's very typical. So we're going to just plug in 2 for x and -2 for y. We're going to get 4 times 2, which is 8, minus 3 times 4, which is 12, over 4 times -8, plus 6 times 4. And that ends up being, let's see, 8 minus 12 is -4, over -32 plus 24 is -8. It ends up being 1/2. So the equation of our tangent line is y plus 2 equal to 1/2 times x minus 2. I would probably leave it like that. Well, I don't know. I might leave it like that. I'd probably solve for y because that's pretty standard to do. So I'd probably rewrite it as y equal to 1/2 x. 1/2 times -2 is -1, and then we subtract another 2 and get -3. I should point out, because sometimes it's nice. So here it wouldn't have made sense really to do this, but if we had wanted to, after the very first step, we could have just plugged in x equal to 2 and y equal to -2 to find the slope at that particular point. So if we actually plug in -2, I'm going to write it. Do I have room? Yeah. If I plug in the point, sure. I'm like trying to find a good spot to do it. If I plug in the point 2, -2 right here, I get 3 times 4, which is 12, plus 2 times -2 cubed is, sorry, 4 times -2 cubed is going to be -32 y prime, equal to 4 times 2 is 8, minus 6 times -2 squared is 6 times 4, which is 24 y prime. And then if you solve for y prime, you're going to get the same answer. If we add 32 y prime to the side, we're going to get 8 y prime on the right. And if we subtract 8 on the left, we're going to get 4. And oh yeah, we're going to get y prime equal to 1/2. And that would have totally been what I would have done if I only had to find the slope of the tangent line at one point. Because we're like, oh, I take the derivative, plug in the point. But since I have to do it at multiple points, it usually is more efficient to actually find the derivative in terms of x and y, and then plug in the various points. So there's the equation of the tangent line when the point's 2, -2. Let's go ahead and find the other two lines, which are actually going to be pretty easy. Well, maybe. So here's our derivative again. And now let's look at the point. Which one do I want to do first? Let's look at the point 0, 2. If I plug that in, the slope is going to equal 4 times 0 minus 3 times 0 over 4 times. It really doesn't matter what the bottom is as long as it isn't 0. Because once the top is 0, oh, I think it was actually 0, -2. Yeah, it was. But it still doesn't really change anything. Right? Once the top is 0 and the bottom isn't 0, 0 divided by not 0 is 0. Welcome. Let me see your symptom survey. What does it mean if the slope is 0? What kind of line do we have? Yeah, horizontal. So what's the equation of the line? Oh. Thanks. What is the equation of the line? Exactly, right? It's definitely y equals something, and we know it has to be -2 because it's going through the point -2. And then at the point 2, 0, something similar is going to happen. Well, similar but different. So at 2, 0, we're going to get 4 times 2 minus 3 times 4 over 0 plus 0, which is not 0 over 0. What does it mean when this? What does that mean? I've got -4 divided by 0 for my slope. Is that one more time? Yeah. It means my slope is undefined, which means we have a vertical line. And what's the equation of our vertical tangent line? Well, horizontal lines are y equals something, vertical lines are right. So our equation is going to be x equal to 2. Now, here's what's kind of cool about living in a modern age. Back when I was a student, probably, I don't know, maybe there would have been a way, but as far as I know, when I was a student, there wasn't really any way we could have reasonably graphed this equation. It's pretty complicated. It's not very nice, but we don't live back 20 years ago. We live now. We have cool tools like Desmos. Whoops, that's not the thing I meant to click on. Sure, let's see here. So check this out. Not that specifically. So we can actually just type in the equation. X cubed plus y to the fourth equal to 2x squared minus 2y cubed. And we can see that, oh yeah, it's definitely not a function, right? It certainly fails the vertical line test, but it does have tangent lines. And for the most part, y does depend on x, right? If you know what x is, y has probably one or two possible values. So it still makes sense to be thinking about y being dependent on x. We throw around the word function, right? Even though we shouldn't, right? We pretend in this situation that y is a function of x because it's convenient to do so when we find the derivative implicitly, but really it's more that y depends on x. Also, what's cool is we can actually kind of see the tangent lines. Let's zoom in a little bit here. So we've got the point 2, 0. Do we have the point 2, 0? Can I click on it? Why can't I click on you? What's your problem, graph? I guess I can't click on it. That's fine. Be that way. I can still graph my tangent lines. So I've definitely got x equal to 2. There's your vertical tangent line at the point 2, 0. Oh, cool. And we've also got y equal to -2. Yep, looking pretty good. There's my horizontal tangent line right there at the graph, right? It's literally tangent to the graph as it should be. And then lastly, we have, what is it? Y equals, I forgot what it was, 1/2 x minus 3. Oh, look, there it is. Perfectly tangent to that point right there. Kind of neat. So if you're interested, if someone gives you something like this, you can kind of graph it and see something kind of interesting. Now, I will tell you, if your equation is too crazy, it's going to look super wacky. Like I was doing one that had like a tangent and an e to the x in it, and it was just like, it was totally bananas. So it works best if you really only got like powers of x and y. If you've got other things going on, it's going to look kind of super bizarre, but it's neat. It's kind of cool to see that what you're doing actually has some physical interpretation that is meaningful, other than just, yeah, we found a derivative. There's a slope. Okay. It really is a thing. Questions about that? So last time, people had asked about finding the derivative of inverse trig functions, and we kind of got there at the end, but it was a little hurried. So I feel like we should backtrack a little bit to talking more about derivatives of things with logarithms, and then, well, you'll see what I mean. So last time we did say the following thing. We found for sure that the derivative, this pen, so I like dropped this pen on the floor and like push the thing in, and like it kind of works, but doesn't work as great as the other ones. But I don't want to just say you don't work anymore. You're still a good pen. I like you. All right. So last time we found that the derivative of the natural log of x was 1 over x. I can certainly show that again if you guys would like, or we can just believe it. Okay. So then we just believe it. So then, just like with any function we know how to differentiate, there's a chain rule version of it. Derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Or as people often prefer to write, it's the derivative of the stuff divided by the stuff. I will usually express things in this way to kind of really emphasize the fact that after we do the derivative of the outer function, we then multiply by the derivative of the inner function. So I usually tend to think of things or express things this way, but it's really okay to simplify it this way. Probably even preferred, I would argue. So let's do some derivatives. What if our function is y equal to the natural log of sine of x? Let's find that derivative. Well, it's going to be 1 over sine of x times the derivative of sine of x, which is cosine of x. And while you certainly could leave this as 1 over sine times cosine, or even as cosine over sine, it would be much nicer to write this as what? What's cosine over sine also known as? Right. So this is cotangent of x. And honestly, the reason I'm really kind of mentioning this right now is because later on in 21B, when you start talking about antiderivatives, you're going to want to know that the antiderivative of cotangent, or you're going to learn really, the antiderivative of cotangent is the natural log of sine of x, because the derivative of the natural log of sine of x is equal to cotangent of x. But this idea worked, regardless. So let's say we had y equal to the natural log of x cubed plus e to the x. The derivative is going to be just 1 over the stuff times the derivative of the stuff. And again, I probably would write this as 3x squared plus e to the x over x cubed plus e to the x. And no, that does not simplify any further. That is as simple as it gets. But then people like to ask crazy questions like, what have I got here? Sure, yeah, that's crazy enough. Let's say I want to find, do I have enough room? Yeah, enough room. Let's say my function is the natural log of x cubed times secant of x divided by e to the 5x times the square root of x cubed minus 1. I certainly could do this the terrible way. I could say, okay, fine. I'm not actually going to do it the terrible way, but I could totally say, all right, well, my derivative is going to be 1 over the stuff times the derivative of the stuff. The problem is, as you might notice, taking the derivative of that stuff is awful, right? It's going to be a quotient rule, a couple product rules, a couple chain rules, right? There's a whole bunch of work to do taking that derivative. So the whole idea here is you don't want to do that. You want to make your life easier. And the way we're going to make our life easier is by remembering that we have some rules for simplifying logarithms. Specifically, log of a times b is equal to log of a plus log of b. I should throw in a base, right? I'm writing that as if it's log base 10, but we can really write it with any base. So log usually base b. And log base b of a divided by b is equal to the log base b of a minus the log base b of b. The lowercase b and the capital B have nothing to do with each other. They're just typical letters. And then finally, log base b of a to a power equals that power times log base b of a. So we are definitely going to use those rules to make what's inside the logarithms as simple as possible. We're going to have more logarithms, but they're going to be much, much, much easier to differentiate. So let's go ahead and rewrite this thing, and we're going to break it up. So we've got y equal to the natural log of x cubed times secant of x over e to the 5x times the square root of x cubed minus 1. So I'm going to show this in a couple steps, but then I'm going to say something again about how you can do it in kind of just 1 or 2 steps. So I'm going to break this apart as the natural log of the top, x cubed times secant of x, minus the natural log of the bottom, natural log of e to the 5x times. I'm going to write square root of x cubed minus 1 as x cubed minus 1 to the 1/2. Couple things to observe at this point. I can't bring any powers down yet, because to be able to bring the power 3 down in front, it has to be the power on the entire argument of the logarithm. Same deal here. I can't bring that 1/2 down yet. So what I'm going to do, I'm going to use the product rule for logs. the natural log of this times this is equal to, we have the natural log of x cubed plus the natural log of secant of x minus, I'm going to do the same thing here. Now be extra careful here. I'm going to make a mistake. The natural log of e to the 5x plus the natural log of x cubed minus 1 to the 1/2. And what's the mistake I've made? What did I forget to put in? Yeah.
Put the parentheses on the right side.
Exactly. I need parentheses around this because I need minus the natural log of all that stuff. And the natural log of all that stuff is natural log of this plus natural log of this. I need to subtract all of that. So here's what I usually say. You can jump. In fact, I'm going to rewrite this even though I would normally not write this stuff. I'm going to write it like this. Natural log of x cubed plus the natural log of secant of x minus the natural log of e to the 5x minus the natural log of x cubed minus 1 to the 1/2 power. Here's what I want you to see. When you have the natural log or any log base of some things multiplied or divided together, every factor that's in the numerator ends up in a logarithm with a positive coefficient. Every factor that's in the denominator ends up in a logarithm with a negative coefficient. It's always going to happen because it's always the stuff on the bottom that's getting subtracted and the stuff on the top that's getting added. So in my opinion, you can jump straight from this first step to this step here. You could probably even jump to the last step, which is where we bring down all the powers. So I'm going to do one more step because I would rather not take the derivative of the natural log of x cubed. Right? I could. It'd be 1 over x cubed times 3x squared. But I'd rather make my life as easy as possible and rewrite this as 3 times the natural log of x plus the natural log of secant of x minus 5x times the natural log of e. Or really, you could say, I know that's just going to be 5x because natural log of e to the something is just the something. Natural log of e is 1. Minus 1/2 the natural log of x cubed minus 1. Notice, I haven't taken a derivative yet, right? So you either want to be simplifying or differentiating, but you shouldn't be mixing and matching. Right? I don't want to, I know this natural log of secant of x has been the natural log of secant of x every step, and we're eventually going to differentiate it. But if you're not differentiating everything else in that step, you should just be simplifying. So the things that are already simplified just get to stay the same. Now, finally, we're going to differentiate. So we don't want to write the derivative until we're actually taking the derivative. So 3 hangs out, and the derivative of the natural log of x is 1 over x. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And the derivative of secant of x is secant of x times tangent of x. Minus the derivative of 5x is just 5. Minus 1/2 times the derivative of the natural log of x cubed minus 1 is 1 over x cubed minus 1 times the derivative of x cubed minus 1, which is 3x squared. And normally I wouldn't really simplify this, but there's a couple really easy things we can do. We can rewrite this as 3 over x. Here a secant cancels, and we're left with just tangent of x. Minus 5. And then here we can rewrite this as minus 3x squared over 2 times the quantity x cubed minus 1. And that's how I would do this problem. So if you've got log, and I've definitely asked questions like this on tests and I've taught, Calc 1. And whenever someone asks you to take the derivative of the natural log or log base 2 of something really, really gross, they mean for you to do this. Really. They really would really prefer that you do not do it the hard way because it's not fun to grade. So what time is it? Okay, we got lots of time. So that's kind of the deal with logarithms. Well, with natural logarithms, just the derivative is 1 over the stuff times the derivative of the stuff. But what if our base is different? What if we want, say, to find the derivative of log base 2 of x? Oh, and I should actually ask. Well, no, I shouldn't ask. I'll just do it. So how are we going to do that? That's not the natural log of x. So this is where it's probably best if we just use the change of base formula. So there is a formula, change of base formula, which I'm happy to explain if anyone wants to see it. If you have log base b of x, it's equal to, really you can pick any base you want. The base we're going to choose is the natural base because it's the nicest. You can rewrite log base b of x as the natural log of x divided by the natural log of b. I'll just point out you can actually use any base you want. So the more general version of the formula is, say it's log base a of x over log base a of b. This is especially useful if you're trying to evaluate something like log base 8 of 32. What base do 8 and 32 have in common? 8 to the power of what? I mean, it's a power of 8. That's not the answer I'm looking for, though, right? 8 to the first is 8. But 8 is something to the third power. 2. And 32 is also 2 to some power. It's 2 to the fifth. You could totally rewrite this as log base 2 of 32 over log base 2 of 8. And log base 2 of 32 is 5. And log base 2 of 8 is 3. And it's totally true that log base 8 of 32 is equal to 5/3 because 8 to the 5/3 power is equal to 32. So that's a very convenient way of simplifying or finding the value of a logarithm where the base and the argument have a common base by rewriting it using the change of base formula with that common base as the base. That's not what we're doing here. It just seemed like a relevant time to mention it. Why does this formula actually work? Well, here's why it works. I know I said I was going to ask if you guys want to see it, but I'm just showing you. Let's say we have y equal to log base b of x. I can rewrite that as an exponential equation. What's my base? It's b. What's the power? It's not 1. It's one of the things that's in this expression. Is it y or is it x? It is y. And the way I always remember this, well, the way I actually really remember it is I draw this little picture. I go b to the y equals x. But one other way people often think about this is when people talk about logarithms, many people say the logarithm is the exponent. That always kind of feels weird to me to say, but it's actually true, right? When you're talking about the logarithm, you're saying, oh, the logarithm really is the exponent, where the base is b, the value you get at the end is x, and what it's equal to, y, is the exponent that gets you there. So b to the y should equal x. And honestly, what I keep in mind is the fact that log base 2 of 8 equals 3 is equivalent to 2 to the third equals 8. That's the logarithm that always lives in my head. So then we can take the log of both sides. Pick any log base you like. I'm going to pick the natural base e. So I take the natural log of both sides. What can I do with that y? I can use my logarithm rules and say, oh yeah, the y gets to come down in front. Then I have y times the natural log of b equal to the natural log of x. But then I can solve for y and say y equals the natural log of x divided by the natural log of b. But remember, y was equal to log base b of x. So that's why the change of base formula actually works. So why is that useful to us? Well, now we can go back up to this problem and say, well, I'm just going to rewrite log base 2 of x. I'm going to rewrite this as the derivative of the natural log of x divided by the natural log of 2. No, I don't need to use the quotient rule here because I can really think of this as the coefficient 1 over natural log of 2, which is a constant. I don't know what it is, but it's something, times the natural log of x, which is not constant. And then the derivative of a constant times a function is the constant times the derivative of the function. So the derivative of log base 2 of x, usually we write it as 1 over 1 over x natural log of 2. That's typically the order we like. Like, I don't know why that's the order we do it in, but it's definitely the order we do it. We usually write the x before the natural log of 2. But we do write it all in the denominator. Can you explain how you did the constant and natural log one more time? Do you mean like how I went from here to here? Is that what you're asking about? Yes, okay, sure. So what I'm really trying to do is I'm trying to make my life easier. Like that's, I mean, that could be the title of this class, how to make your math life easier, right? I'm trying to do it the easy way, not the hard way whenever I can. Unless it makes sense to do it the hard way, because sometimes the hard way shows us something. But let's go back here and say, okay, I was trying to take the derivative of the natural log of x over the natural log of 2. Well, let's pause on that for just 1 second, because I feel like this is something we should look at anyway. So what's the derivative of x to the 9th over 6? Could I use the quotient rule here? Totally, right? And it would be the bottom times the derivative of the top minus, what would you have? Yeah, the bottom times the top minus the top times the derivative of the bottom. And the derivative of 6 is what? 0. All over the bottom squared. But look what ends up happening. This part here, this is just 0. And I end up getting, I'm not going to multiply this out. I get 6 times 9x to the 8th over 6 squared. But I can cancel one of those 6's. So I'm really left with 9x to the 8th over 6. Or as I would say it, I just took the derivative of the top part and left the bottom alone. Is that a question or just stretching? Okay, cool. So more generally, when I see something like this, like if I was taking the derivative of, I don't know, x to the 11th power over 5, I was be like, I know it's going to be 11x to the 10th over 5. And the rule, the way I'm usually thinking about it is to say, well, I'm really not dividing by 5. I mean, I am, I'm dividing by 5. But specifically, and I know this is going to sound kind of dumb, division is multiplication. Multiplication is division. They're just division by a different thing or multiplication by a different thing. Dividing by 5 is the same as multiplying by 1/5. Multiplying by 8 is the same as dividing by 1/8. The only exception is if you're multiplying or dividing by 0. 0 is the exception to the rule, but every other number you can always change thinking of it as multiplication to thinking of it as division or vice versa. So I'm not going to think of this as dividing by 5. I'm going to think of this as multiplying by 1/5. But then I know I have a rule for when I multiply by a constant. The rule for multiplication by a constant is, oh, the constant hangs out. And we take the derivative of the function part. And the derivative of x to the 11th is 11x to the 10th. And you could totally leave it that way, or you could write it as 11/5 times x to the 10th, or you could write it as 11x to the 10th over 5. Either way would be acceptable. This first is probably. So back to the problem at hand, the derivative of the natural log of x over the natural log of 2. It's super duper important that you recognize that the natural log of 2 is a constant. Right? There's no x's in there. It never changes. It's always approximately 0.69. I'm going to think of this as 1 over natural log of 2 times the natural log of x. And I'm going to point out, oh yeah, this whole thing here That's a constant. It never changes. And the derivative of a constant times a function is the constant times the derivative of the function. But the derivative of the natural log of x is 1 over x. And then we write it typically as 1 over x natural log of 2. And I would encourage you all to apply this thinking in general, right? Not just for this, but for anything. If you ever see a problem where it's like, okay, I want to find the derivative of, I don't know, e to the x cosine of x squared over 5, I don't have to use the quotient rule here. The bottom's just 5. It's just going to stay 5. I can do the derivative of the top, which is going to be kind of a pain in the butt. It's going to require the product and the chain rule. But the derivative of e to the x times cosine of x squared is going to be derivative of e to the x is e to the x times, leave the other one alone, cosine of x squared. Plus, then we do it the other way. We leave the e to the x alone, which is e to the x, times the derivative of cosine of stuff is negative sine of your stuff times the derivative of your stuff. But I didn't even think about the 5 because dividing by 5 is really just multiplying by 1/5. That's just going to stay as is. So if you ever have a quote unquote quotient where the denominator is a constant, you can just leave it as is and completely ignore it. So hopefully that, I know it's a long answer to your question, but I think that's a pretty good explanation of what's going on there. And now what we can say very, very generally is if you're taking the derivative of, say, log base 5 of x, we don't have to go through this process again, right? I could just take the previous work I did and replace the 2 with a 5, and we're going to get the same sort of answer. The derivative is going to be 1 over x natural log of 5. Or more specifically, I should say more generally, the derivative of log base b of x is 1 over x times the natural log of b. And it also works for the natural log. Right? You could say, well, okay, James, the derivative of the natural log of x is the derivative of log base e of x, right? It's just an abbreviation for log base e. And then we can rewrite that as 1, well, we find the derivative as 1 over x times the natural log of the base of the natural log of b is just 1. So it does work for any base. We just don't usually think of it for the natural base because we know the rule is derivative of 1 over x. And then, of course, just like with every function we ever learn how to differentiate, once you know how to differentiate log base b of x, you can then say, well, James, what about like a chain rule kind of question? What about the derivative of, oh, that's nice there, James. What about the derivative of log base 7 of x to the 5th plus 9x? So here's the way I typically think about bases other than e. I know that when my base is not e, I'm going to end up dividing by the natural log of that base. Other than that, the rule is kind of the same. So I know the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. I know the derivative of the log base 7 of some stuff is going to be 1 over the stuff times the derivative of the stuff. And then I also have a 1 over the natural log of the base. And I know that looks terrible. I would definitely, I would most likely write this as 5x to the 4th plus 9 over x to the 5th plus 9x parentheses times the natural log of 7. That's probably the smoothest way of writing it. So why don't you guys try this one? I'm going to go, it's a little early for that. Okay, I'm using the rest of my notes. So why don't you guys try finding the derivative of log base 3 of x to the 4th plus e to the 2x plus 1. I'm going to use the restroom real quick. I'm an old man. I feel time. Apparently. Looks like a winner there, yeah. Yeah, anyone on Zoom, you're always welcome. If you want to like type your answer to me, I know this one's a little pain in the butt to type, but if you want to like type your answer to me, I'm happy to see it. No one else can see your answers, so you're welcome to. So let's see. So if I'm doing this one, I'm doing 1 over my stuff, x to the 4th plus e to the 2x plus 1. I suppose I could really, if I wanted to, I could try to do it all in one step so I didn't have to rewrite it. So it's 1 over the stuff. Then we also need a natural log of 3 in the bottom. And then we're going to multiply by the derivative of the stuff. Instead of multiplying out here, let's just put it up here. So we're going to get a, I already kind of screwed it up with the 1 there. Okay, I'm gonna change that 1 to a 4. We're going to get a 4x cubed plus the derivative of e to the 2x is 2e to the 2x, or e to the 2x times the derivative of 2x. That's how we do the derivative of that. All right, let's move on. I know we're slowly working up to the derivatives of these inverse trig functions. There's lots of other things in between here and there, so it's not like we shouldn't skip them. There's that. Yeah, that's interesting. Okay, so there's kind of 2 ways of talking about this next part. I'm going to remind you guys. I know we just did an example, but it still is worth remembering. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Or you might see in the textbook, if u is a function of x, then the derivative of e to the u is equal to e to the u times u prime. That's how they usually, usually u is what they use for stuff in textbooks often. So how would we take the derivative of, say, 4 to the x. Well, there's actually probably two good ways of doing this. I had never learned this way I'm about to show you until maybe last year when I saw it in the 17 series, actually. I'm going to show you both ways because your teachers might expect you to do one way or another. Really, either way should be fine, but let me show you what I mean. So one way of doing this, which is probably kind of the less convoluted way, actually, is to say, well, look, y equals 4 to the x. I can rewrite that as y equals e to the natural log of 4 to the x. Because it's definitely true that, I should in fact point out here, recall that e to the natural log of x is equal to x, or more generally, e to the natural log of some stuff is just equal to the stuff. That's the whole idea here. So now check this out. E to the natural log of 4 to the x. What can I do with that x? Oh, we can come down in front of the natural log of 4. Right? If you ignore the e for a second, you've just got natural log of 4 to the x, and the power can always come down in front of the logarithm. So I can rewrite this as y equal to e to the x times natural log of 4. But now we know how to take the derivative of e to the stuff. The derivative of e to the stuff is just going to be e to the stuff times the derivative of the stuff. Okay, everybody should be able to tell me what is the derivative of x times natural log of 4. Or let me say this a different way. What's the derivative of a constant times x? The derivative of a constant on its own is definitely 0. Let me ask you a different question. We'll come back for sure. Let me ask everybody. What's the derivative of 6x? Right, it's totally 6. And the derivative of, say, 81x is definitely, or any constant times x, the derivative is just the constant. So here, the derivative of x times natural log of 4 is, it's not 1. What's the constant x is being multiplied by? What is the constant that x is being multiplied by? It definitely is natural log of 4. Natural log of 4, I don't know what it is. It's about 1.38, I think. But natural log of 4 is a constant, right? It's never changing. It's a number, right? It's some number. It's some transcendental number. But it's a number that never changes. But is there an x there? No, there isn't an x or variable. It's not changing. It is a constant. So that part there is constant. And the derivative of a constant times x is just the constant. I know for natural log, it always feels kind of confusing because it just feels like there's some sort of function thing. And the natural log of x is definitely a function. But when you take the natural log of 4, it's just a value. So a couple last things here. I don't want to leave my answer like this because I'm going to put this x back up there and rewrite this as y prime equals e to the natural log of 4 to the x times the natural log of 4. And then finally, e to the natural log of 4 to the x is just 4 to the x. This is really equal to 4 to the x times the natural log of 4. It's kind of a lot. What I want you to see here is that the derivative of 4 to the x is just 4 to the x times natural log of 4. Let's do this for another problem that's a little more complicated. Let's say we have y equal to 5 to the x to the 4th. and I want to find the derivative of this. So again, I'm going to do the same sort of thing. I'm going to rewrite this as y equal to e to the natural log of 5 to the x to the fourth. And then the x to the fourth gets to come down in front of the natural log. So this becomes, gosh, my mask got itchy all of a sudden. Okay. Y equals e to the x to the fourth times the natural log of 5. And I want to ask everybody, what do we know about the natural log of 5? It's a constant. Natural log of 5 is a constant. So we're going to remember, we're going to pretend it's like 2. Right? You could even just say, okay, I know it's 2. It's not actually 2, but like, okay, whatever. So then we're going to start finding the derivative. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Oops, I forgot to write the derivative symbol over here. Okay, so now, as I move to the next step, I'm going to do 2 things. I'm going to start so here's the thing you should get to do automatically. You can totally be like, okay, I'm kind of done with having done this. I want this to become what it was before, which is 5x to the 4th. I don't think you need to show any steps personally, but I'm going to show the steps so everyone can see them. I'm going to put this x to the 4th back up on as a power of 5. So that part's going to be e to the natural log of 5 to the x to the 4th times, what's the derivative of x to the 4th times a constant? Well, what's the derivative of x to the 4th? And what's the constant do? Right. The phrase I've come up with is the constant hangs out. So constant multiples hang out. They don't go away. They don't change. So, and there's our derivative. Oh, but we want to do one more thing. We want to rewrite e to the natural log of 5 to the x to the 4th it as just 5 to the x to the 4th times 4x cubed times the natural log of 5. So here's what we see happening when our base is not e. In fact, let me just show you for contrast. If I was going to take the derivative of e to the x to the 4th, what would the derivative be? Well, the derivative of e to the stuff is e to the stuff times what? The derivative of the stuff. So here's kind of the difference I'm seeing. The derivative of 5 to the stuff is 5 to the stuff times the derivative of the stuff times the natural log of 5. Whereas the derivative of e to the stuff is just e to the stuff times the derivative of the stuff. If you really, really wanted, you could toss in a natural log of the base, but you don't need to because the natural log of e is just 1. So this is kind of our general rule here, is that we know the derivative of e to the x is e to the x. In fact, I'm not going to write this all. I'm going to write this on another page here. So let me stop writing that. I'll just say that the derivative of stop writing, James. I want to write it all on one page. So like I'm just going to repeat the same writing again. That seems kind of silly. So here's what we have. Here are our rules for logs and exponentials. It's kind of a bit. So if your function is e to the x, the derivative is e to the x. If your function is some other base to the x, the derivative is a to the x times the natural log of that base. If your function is the natural log of x, the derivative is 1 over x. And if your function is log base b of x, I should have used b there, but I didn't, sorry. The derivative is 1 over x natural log of b. So basically, when your base, if it's an exponential function, if your base is different, you multiply by the derivative, the natural log of the base. And for a logarithmic function, if your base is different, you divide by the natural log of the base. And that's true whether your functions are simple like this, or if they are chain rule versions like this. So if your function is e to the stuff, your derivative is e to the stuff times the derivative of the stuff. And if your function is a to the stuff, you're just going to have the same sort of pattern, except you're also going to get the natural log of a in there. You're going to get the derivative being a to the stuff times the derivative of the stuff times the natural log of a. And then the same sort of deal for the logarithmic functions. If your function is the natural log of some stuff, the derivative is 1 over the stuff times the derivative of the stuff. And again, if you prefer, you can certainly write that as the derivative of the stuff divided by the stuff. And then finally, if your function is some other base, log base b of some stuff, it's going to be 1 over the stuff times the derivative of the stuff, and then also divided by log, not log, natural log of the base b. And again, you could probably compactify that a bit. Now, I should mention, while it's certainly worth knowing all of these, no, I should say, you do want to know all these. And really, here's what I would remember these, right? I know the derivative of e to the x is e to the x. I know the derivative of a to the x is a to the x is natural log of it. And then if I know a derivative, I know its chain rule version, right? If I know the derivative of a to the x is a to the x times natural log of a, I know that the derivative of a to the stuff is just the same thing, except tack on the derivative of the stuff at the end. Right? It's a to the stuff times the natural log of a times the derivative of the stuff. So once you know the chain rule, you know how to do the chain rule for any function. It's just how the regular function works, but more. Excuse me. There was something else I wanted to mention. Is that your teacher might show you how to do a function, the derivative function like this, a different way. So let's say our function was, let's say it's 10 to the tangent of x. We could take the derivative just using the rule we've developed, which is that, okay, I know the derivative of 10 to the stuff is going to be 10 to the stuff times the natural log of 10 times the derivative of the stuff, which is secant squared of x. However, some people, instead of doing it this way, right? So some people might actually have you write it out as e to the natural log of 10 to the right and do the whole thing we did before. So one option is to rewrite this as e to the natural log of 10 to the tangent of x, and then rewrite that as e to the tangent of x times natural log of 10. I will say, I haven't seen this as much in the 21 series. Right? I've seen a couple teachers do this once or twice, but most teachers don't have you do this. Most teachers either have you memorize the rule this way. It's like, okay, I know that for my base that's not e, it's just the same expression occurring, natural log of the base, derivative of stuff. But there's another way. I know. The other thing I want to say is that when you're whenever you differentiate something that's exponential, meaning right, you've got something where you've got variables in the exponents, that same exact expression always pops up in the derivative, right? The derivative of e to the x is exactly the same. The derivative of a to the x, oh, there's an a to the x, yeah, there's some other pieces. The derivative of e to the stuff, oh, you get an e to the stuff. The derivative of a to the stuff, oh, you get an e to the stuff, right? Every time you differentiate something that's exponential, you always get exactly the piece you started with, times some other pieces. So here's the other way people might show you how to do this kind of problem. Instead of memorizing a rule or rewriting it as e to the natural log of whatever, they might have you do this, which is a nice way of doing it as well. I'm going to write it as y equal to 10 to the tangent of x. And what I'm going to do is I'm going to take the natural log of both sides. So I'm going to have the natural log of y equal to the natural log of 10 to the tangent of x. And the whole reason for taking the natural log of something most of the time is it allows us to bring the power down in front. So I'm going to rewrite this as natural log, natural log, let's write down here. Natural log of y equal to tangent of x times the natural log of 10. And now we're going to differentiate both sides using implicit differentiation. So what's the derivative of the natural log of some stuff? 1 over the stuff times the derivative we're actually trying to find, right? Y prime is what we're looking for. It better show up if we're trying to find y prime. And then on the right-hand side, what's the derivative of tangent of x? You definitely want to know that one. You want to know all the true derivatives. Derivative of tangent of x is right. So the derivative of tangent of x times a constant is secant squared x times the same constant. Finally, we solve for y prime by multiplying both sides by y. So we get y prime equal to y times secant squared of x times natural log of 10. But we don't leave our answer this way because if our original function was a function of x, our derivative should also be able to be expressed purely as a function of x. So finally, we replace y with what it's equal to. Y is equal to 10 to the tangent of x. So it's going to go in right there. Say, oh yeah, our final answer is that y prime is equal to 10 to the tangent of x times secant squared of x times natural log of 10. The same answer we got up there, but found in a different way. That is often how people show students how to do this at first. But honestly, I think the expectation is if your base is a constant, so if you've got 10 to the sum function or 2 to the sum function or 5 to the sum function, the easiest thing to do, the most efficient thing to do is to memorize the process, right? The derivative of 10 to the something is 10 to the something times the derivative of the something times the natural log of 10. But you can't use that process for the next example. Sorry, you can't use that formula, I should say, for the next example. So let's say instead of your base being a nice constant, you now have a function to a function. Function raised to a function. Let's say we want to find the derivative of, we always start with x to the x, but okay, fine. It's less exciting, but fine. We want to find the derivative of y equal to x to the x. We really want to be super extra clear about this. None of the formulas we have so far would deal with this because this actually isn't anything we've seen. It's not an exponential function because your base isn't a constant. And it's not a polynomial function because your power isn't a constant, right? You definitely cannot say it's not true that y prime is x to the x, right? Pretending like it's an exponential, or it would just be like, oh, it's the same thing we started with. It's not x to the x times the natural log of x if you maybe want to try and use the fancy rule. And it's definitely not x times x to the x minus 1. By the way, x times x to the x minus 1 is just x to the x because it's x to the first times x to the x minus 1. It's definitely not. None of those answers are right. The way we're going to find the derivative of this is the same way we found the derivative of the last one we did, the second way. We're going to use this process. And this process is called logarithmic differentiation. Because you're literally taking the log of both sides and then differentiating. I should say, you're taking the log of both sides and then simplifying and then differentiating, right? The simplifying there is the key step. So, step 1. I should point out, someone might try and make this difficult. Someone might write on an exam, I feel like the people hopefully wouldn't, but someone might try and give you this question on an exam is like, take the derivative of x to the x. And if they write it that way, you have to be proactive. It's like, oh, I think I'm supposed to use logarithmic differentiation because it's, you know, a function to a function. But before you can do that, you really need to rewrite it as, okay, well, I'm going to have y equal to x to the x, and then I want to find y prime. But you really, 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 really have to have the equality there equal to something else so you can take the natural log of both sides. Right? If you just have this, you can't just take the natural log of it. You also need the natural log of y on the other side to differentiate. So if someone writes this, they're kind of whatever. So if someone writes that, hopefully they will. But if you do, you'll know what to do. You'll say, okay, I know that for a function to a function, I have to write it as y equal to the thing. And then we're going to take the natural log of both sides. Why did I do that? What's that going to let me do? What's the next step? Exactly. That's the whole, I mean, not always, but like 99 times out of 100, the reason you're taking the natural log of something is so that you can bring the power out of the power. So I've got the natural log of y equal to x times the natural log of x. Great. Now we can differentiate that. The derivative of the natural log of y. So we have to remember that the derivative of the natural log of y is not even implicit differentiation here, right? It is explicit. Y is a function of x. So when we differentiate something with a y in it, y is the stuff. And the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And unlike our previous examples, where we had something like, where'd you get a previous example? Where we were going to be differentiating something like x times natural log of 4, and the natural log of 4 was a constant. That's not the case anymore. Now we're going to be differentiating x times natural log of x, where we definitely do have to use the product rule. So the derivative on the right-hand side is going to be the derivative of x, which is 1 times the natural log of x, plus x times the derivative of the natural log of x, which is 1 over x. We're almost done. I imagine you could skip this next step, where I'm going to do y prime equal to y times the entire right-hand side. I am going to simplify the right-hand side because x times 1 over x is just 1. But I think you can skip that step, or not so much skip as, in addition to doing that, also make the choice or see that I'm going to replace y with what y is actually equal to. So finally, we've got y prime equal to y, which is x to the x, times the natural log of x. Right, that is your, and that's our derivative. So the derivative of x to the x is x to the x times the natural log of x plus 1. There actually is a formula you can memorize for this. I couldn't tell you what it is without deriving it because I've never memorized it because it's not good. It's much more sensible to know how this process works, because this process is useful for other things as well. So yeah, there's a formula for the derivative of f of x to the g of x power. If you see it, don't memorize it. It is not worth your mental energy or space. It is much better to know if you have a function to a function, you can take the natural log of both sides and then just use the rules we already are familiar with. Nice, or fortunately, the process is the same no matter what. So if I want to take the derivative of something more complicated, like say I want to do the derivative of y equals, what do I usually like to do this? Let me see for one sec. Yeah, sure. I like x to the sine of x because it brings up an interesting point. I want to find the derivative of that. You'd like to see it. So what's y prime? Great. Well, someone was nice. They wrote it in the way where I already know I'm supposed to probably take the natural log of both sides because I've got a y equal to a function to a function. So let's take the natural log of both sides. Okay. We've taken the natural log. Before I start differentiating, I'm not going to get carried away. I'm going to first simplify. So the natural log of y still on the left equals sine of x times the natural log of x on the right-hand side. Now we differentiate. The derivative of the natural log of y is 1 over y times y prime. You're going to see that a lot. Right? The derivative of the natural log of y is going to come up a lot in your mathematical career where we're making the assumption that y is a function of x, or actually is true that y is a function of x. And the derivative of the natural log of y is always going to be 1 over y times y prime. On the right-hand side, what rule do I have to use again? Still the product rule. It's almost always going to be the product rule on the right-hand side. Occasionally it might be a quotient rule, something kind of crazy, but it's almost always the product rule. So the derivative sign is cosine of x times, leave the natural log of x alone, plus sine of x times the derivative of the natural log of x, which is 1 over x. If it helps, it's totally fine to be like, oh yeah, this is my f, this is my g, there's f prime times g plus f times g prime. I'm going to do a little simplifying. So I'm going to say y prime equals y times, I can't really simplify that. I'm just going to leave this cosine of x times the natural log of x. But how could I kind of simplify sine of x times 1 over x? I make right as a fraction, right? Sine of x over x. And then finally, I can replace y with what it's equal to. So y prime is equal to y, which is x to the sine of x, times all this stuff. Cosine of x times natural log of x plus and it's a good question in the chat. Is sine of x over x equal to 1? No, it's not. I know why you're probably thinking that though, because okay, we know that the limit as x goes to 0 of sine of x over x is equal to 1. But that's only if x is getting closer and closer and closer to 0. We're not talking about that here, right? We don't know anything about what x is actually doing. We just know that it's a function. So sine of x over x isn't equal to 1. It's just we take the limit as x goes to 0. So that should just stay as sine of x over x. I wanted to point out that just like with the exponential functions where the base is a constant, even in the, I wouldn't call this an exponential function because exponential function really does mean the base is a constant, but for these functions where you have a function raised to a function, you still have the same sort of result in that you always have that thing you started with showing up again. So when you're taking the derivative of x to the sine of x, you can be guaranteed that an x to the sine of x is also going to show up. Let's do one more. One more. In fact, yeah. Why don't you all try taking the derivative of this one? So let's say our function is y equal to cosine of x raised to the x squared power. And I want you all to try taking the derivative of this one using the same process. Start here. That's all I'm going to do. You guys work on that one for a minute or two. want to type your answer to me in the chat, you're welcome to, but it is a little bit lengthy, so don't feel like you need to if it's kind of like this for us. In case you missed it, here is the attendance form one more time. I didn't think about that, yeah. Unless I'm forgetting. Yeah. Sure. So natural log. We're going to change your derivatives. That's totally right. Yep, I would definitely write it like that. All right, let's see what we've got here. So writing this, again, re-expressing it, but natural log of y equals x squared times the natural log of cosine of x. And now that we've gotten the function out of the exponent, we're going to differentiate both sides. So as is usual, the derivative of the natural log of y is 1 over y times y prime. And on the right-hand side, we're going to use the product rule. The derivative of x squared is 2x times the not derivative of the natural log of cosine of x, plus, then we flip it. We do x squared times the derivative of the natural log of cosine, which is 1 over the stuff, times the derivative of cosine, which is negative sine of x. Simplifying. So here's what I would say. I really would prefer not to write, like if I was a student, I don't want to write 2 lines. In my next line, I would do the following. I would write y prime equal to y multiplied by y, but I know y is equal to cosine of x to the x squared power. So I'd be like, okay, it's going to be cosine of x to the x squared. That's the y I'm multiplying by, times all of this jazz over here, which is 2x times the natural log of cosine of x, plus, sorry, not plus, it should actually be really minus x squared times sine over cosine is tangent. That's how I would simplify that. Now, if you want, you can totally write the intermediate step. And the intermediate step would be to say, okay, I've got y prime equal to y times 2x times natural log of cosine of x minus x squared times sine x over cosine x. And then go from there to there. But it's okay to jump straight from there to there if you're comfortable with that. And yeah, that's a good question. While you certainly could write the 2x as the power of cosine there, like you could write this as the natural log of cosine of x to the 2x power, totally unnecessary. Like, and I've never seen anyone do that, so I would dissuade you from doing that. But yeah, it's certainly something, it wouldn't be wrong, it just would be weird. Weird's probably not the right word, just atypical. All right. So here's something that I feel like I didn't learn when I was taking calculus. because, well, I did, but just not in this way. So inverse derivatives, meaning the derivatives of inverse functions. I would probably never use this formula, but there are times when it's useful. So here's an example. Let's take the graph of f of x equal to x cubed plus 1, and also the inverse. So sometimes the inverse is really easy to find. Sometimes it's a whole huge pain in the butt. When you think of an inverse function, you should think of a function that undoes what the original function does. This one, it's probably easy enough to just say the words to figure out what it is. So this function, x cubed plus 1, takes your x, and what does it do first? It cubes it, right? I'm going to take, if I was like, for example, if I was going to plug in 2, f of 2 would be 2 cubed plus 1. I would first cube it and then add 1 after, right? Order of operations. I don't really care that it's 9. But the thing is, I'm going to actually show the work, but you could also in this one just kind of talk out what the inverse is. So the inverse should undo what the function did. This function took a number, then cubed it, then added 1. So how am I going to undo that? Well, first I'm going to subtract the 1. Then I'm going to cube root to undo the cube. So this one is easy enough to say like, oh, the inverse function is, well, first I'm going to subtract the 1, and then I'm going to take the cube root. That's not always a good technique, but it's good here. And you can see that, oh yeah, it's going to undo what I just did. Because if I plug in 9, f inverse of 9 is the cube root of 9 minus 1, which is the cube root of 8, which is 2. So this function did something to x. You got something out. And this inverse function undid what that function did to x. And you got the same thing back you started with. The process, of course, for finding the inverse is to switch x and y and then solve for x. Solve for y, right? You could totally be like, okay, here's the process. Y equals x cubed plus 1. You switch x and y. You solve for y. So y x minus 1 equals y cubed. So y is the cube root of x minus 1, which we are already using the inverse function. So there's your inverse. Great. So here's what I actually care about you seeing, though. And this is actually, I think this is a good time for Desmos. Yeah, I mean, I always think it's a good time for Desmos. So let's graph these things. Let's close these things. So here we've got y equal to x cubed plus 1. And maybe we like to recenter things, please. Yes, thank you. And here we've got y equal to the cube root. Sure. I'll just do that. X minus 1 to the 1/3 power. And as you might be aware, these functions are reflections of each other. Oops, oh, come on. What did I do now? I ruined it. It's over. There we go. These functions are reflections of each other in the line y equals x, which makes some sense because what you're literally doing is you're interchanging x and y. And so you can see that on the original function, you've got the point like 0, 1, and you've got the point 1, 2. Oops. And you've got the point, and it might not be actually on there, but I'll graph it anyway, 2, 9, and so on. And you can't quite see that one. You can't even see it, right? So you've got that point, that point. And on the inverse function, you've got exactly the inverse points, right? Instead of 0, 1, you've got 1, 0. Instead of 1, 2, you've got 2, 1. Instead of 2, 9, you've got 9, 2. Okay, but here's the other kind of interesting fact. There's symmetry here. And so what I really am interested to know about is how does the slope at this point compared to the slope at that point? Well, they're both positive, right? What's interesting is they're actually not like, this is a theorem that I've always been like, how does that work again? They're actually, I believe, reciprocals of each other. So it's true, and I'm gonna look at the answer here. Yeah. So the slope at that point here is, I believe it's 12. Well, in fact, let's just do the work. So let's write some things out. Let me get back to the thing I wanted before. Let's make that big again. So for this function, f of x equals x cubed plus 1, what is the slope? I think I was clicking on the wrong point there. That's all right, though. What's the slope at the point 1, 2? That seems like an interesting question to answer. Well, I can find the derivative. It's 3x squared. And if I plug in 1, f prime of 1 is 3. And I could also ask the question at 2, 9. And at 2, 9, the slope would be f prime of 2, which is going to be 3 times 2 squared, which is 12. For the inverse function, well, the inverse function, f inverse of x, is going to be x minus 1 to the 1/3 power. And the derivative of the inverse function is 1/3 times x minus 1 to the negative 2/3. Or you might prefer to write it as 1/3 times x minus 1 to the 2/3 power. Now we have to be a little bit careful here because the x value I'm going to plug in isn't the same, right? If you look at this for a second, if I'm looking at the point, 1, 2 here, I'm not going to be plugging in x equal to 1 to find the slope there. I'm going to be plugging in x equal to 2, right? The y value for the other point. So I really want to know, okay, what is this? What am I going to get when I find the derivative of f inverse of x evaluated at x equal to 2? Right, because that's the point I'm looking at. And when I do that, I'm going to get 1/3 times 2 minus 1 to the 2/3, which is 1/3. Because 2 minus 1 is 1 and 1 to the power is 1. And likewise, when I evaluate this at, so the notation here is kind of lame. So this other one I did at the point 2, 9, and the derivative was 12. Here I want to plug in, instead of 2, I want to plug in 9, right? Because 9 is the corresponding coordinate. In fact, let me show you again, because I think it's worth really seeing this. And if I'm looking at this point up here, there's 2, 9, where the slope was 12. And now I'm looking at the point 9, 2. And I'm expecting the slope to be 1/12. And it is. Trying to close this. And if we plug in here, we're going to get 1/3 times 9 minus 1 to the 2/3 power. 9 minus 1 is 8. 8 to the cube root of 8 is 2. 2 squared is 4. 4 times 3 is 12. Oh, yeah, it's 1/12. So here's the idea. If you want to find the derivative of the inverse function, it's the reciprocal of the derivative of the original function. But you have to change the inputs, right? So for example, this is where things get kind of a little bit wacky. For this particular example, if I want to find the derivative of f inverse of x at some, say, x equal to a, then that's going to be 1 over the derivative of the function at the corresponding value, right? So for the inverse function, sorry, now I'm getting a little all over the place here. For the inverse function, why do you keep doing that? Right, I'm plugging in, say, this point here, but then I have to find the corresponding y value of it to plug into that there. So I'm not plugging in, say, x equal to 9. I'm plugging in y equal to the inverse value of 9, or the inverse value of x, which I feel like this is the part that makes, oh, sorry, you can't see what I'm writing. I feel like this is the part that makes this formula kind of super weird, is that you're plugging in like this alternate value to the function. So for example, the derivative of f inverse of x at x equal to 9, which is what we found up here, is equal to 1 over the derivative of f of x evaluated at, I should have really written x here, but okay, fine. At, yeah, x equal to f inverse of 9, which is 2. That's the idea. Oh, you can't see the idea. So the derivative of a function is 1 over the derivative of the inverse, but you have to make sure the inputs are right. It's a little weird, and it's a little, really, it's a little unnecessary most of the time, because although this certainly works, it's not particularly, there's other ways to get what we want. So someone asked, is there any way that the inverse derivative would have a 1 over 0 type? Yeah, it is possible that the derivative of the inverse could be undefined. For example, looking back at our graph here, certainly this function at 0, 1, the derivative would be 0, because the tangent line would be horizontal. And at 1, 0 for this other function, the derivative would be undefined, because the tangent line would be vertical. So yeah, you could totally have that happen, that the inverse derivative would have a 1 over 0 undefined type. Hopefully no one's asking you that, but they could. So here is the theorem that we're working at, or working towards. So the slope of, sorry, I keep forgetting you can't see the things if I don't show you the things. So the slope of an inverse function can be found in the following way. The derivative of f inverse at some value b is equal to 1 over the derivative of the function at f inverse of b. Or sometimes you'll write this as df inverse dx evaluated at x equal to b equals 1 over df dx evaluated at a equal to f inverse of b. It's kind of a, I hate to use the word, no, it's not my favorite formula, as you might have guessed, but it does have its uses. You could totally use this formula to find the derivative of an inverse trig function. Is it the way I would want to do it? No, it's not. Usually this type of formula is used more to ask kind of challenging questions. Here's an example. Here's an example of why you might actually want to know this formula and not just have it be kind of ridiculous. So let's find the slope of the tangent to the inverse of f of x equal to x to the 5th plus x cubed plus x at the point 3, 1. So 1, I should mention. Ooh, I'm going to make it. I was going to try to make this harder, but it's fine. So I should mention, I don't know what the inverse of this function is. Right, this function is hard to, maybe impossible to actually express the inverse of. But I do know it's invertible. And the way I know it's invertible is, well, really the way I know it's invertible is because this function is increasing always. Right? If you think about it, x to the 5th from left to right is always getting bigger. X cubed from left to right, always getting bigger. X from left to right, always getting bigger. And if you add things that are always getting bigger from left to right, then they're always getting bigger from left to right. So this function is always increasing. But that means it passes the horizontal line test. The horizontal line test is the test to see if a function is invertible. Just like the vertical line test is the test to see if a function is a function. So if you pass the horizontal line test, it means your flip passes the vertical line test. So your inverse is a function. We're just trying to justify the fact that you can use this formula. So I'm going to say, well, I want to find df inverse dx at x equals 3. And the way I can make this harder is I could say, let's pretend we didn't have this information. Nobody told you it was at the point 3, 1. They just said, I want to find the derivative of the inverse at x equal to 3. So here's what I know. I know it's going to be 1 over the derivative of the function evaluated at f inverse of 3. Okay, well, one of those pieces is easy. They're actually both not terrible, for example. It's going to be 1 over the derivative of, well, let's see. I can actually show you this on Desmos. Oh, cool. This is going to be kind of cool, I think. You might not agree. That's fine. The derivative here is going to be 5x to the 4th plus 3x squared plus 1. Evaluated at f inverse of 3. So a lot of the times they want you to actually guess what f inverse of 3 is. So here's the idea. F of something has to equal 3 is equivalent to f inverse of 3 equals the something. So the point is you have to kind of guess if they're giving to you, what can you plug into this function and get 3? 1, right? And it's usually going to be a pretty easy thing to guess. It's going to be like 0 or 1 or -1. So, oh yeah, that's going to be 1, which means that's going to be 1. So we're really doing this at x equal to 1. So then you plug in 1, you get 1 over 5 plus 3 plus 1, which is 1/9. Let's see it, because I do think it's worth seeing these things, because I feel like maybe I'm just bringing my own personal bias to this. I feel like this is challenging and kind of, it's just weird to think about. Delete all these things. Okay, so here's the function we just found the derivative of at first. It was x to the 5th plus x cubed. Oops, wow, okay, that's not, let's be a little bit careful there. X to the 5th plus x cubed plus x, which you can see is always increasing. And we also plugged in 1 to its derivative, and its derivative was 9. So at 1, so let me draw you the tangent line. So at 1, the slope of the tangent line is 9, and the coordinate is 1, 3. So we'd have y minus 3 equals 9 times x minus 1. There's your tangent line at the point we're looking at. 1, comma. Why do my values look so, oh, it's like way up here. So there's the tangent line. Kind of funky. Not funky, just kind of hard to see. Okay, but then what's cool about this is we can also you can easily draw an inverse function on Desmos. Switch x and y. So x is going to be y to the 5th plus y cubed plus y. There's your inverse function. And at the point, instead of 1, 3, at the point 3, 1, the slope of the tangent line is definitely 1/9. Y minus 1 is equal to 1/9 times x minus 3. Oh, come on. Why am I having so many troubles here? This is why. Why is there parentheses there? Sorry about that. I'm having troubles where I shouldn't. But there it is. Look, at that point, the slope of the tangent line is definitely 1/9. So these inverse functions really do have reciprocal slopes at matching up points.